Hydration is the addition of water across a carbon-carbon double bond. It accomplishes the conversion of an alkene to an alcohol. The typical reagents are water and some non-nucleophilic strong acid, H2SO4, H3PO4, etc. Anything that doesn't have a nucleophile like chloride or something present. And we start with an alkene, we add the elements of water. It's a Markovnikov addition, which means the regiochemistry is such that the hydrogen that's added to one carbon goes to the carbon that has more hydrogens already, and the OH, the non-hydrogen group, adds to the more highly substituted carbon from the alkene bond. This reaction doesn't have stereochemistry, or as we'd say, not stereospecific, meaning that the H and the OH could end up in any pattern relative to one another. We say it's an addition reaction because we're adding elements to a molecule, but we're not taking anything away. The mechanism is an important one for us to know, and it explains the regiochemistry. Specifically, let's start off with an alkene that's asymmetric, or has more things on one side than the other. So we'll use simple propene. The first thing that we're going to do is start by protonating our alkene. And you remember that the first thing that happens in any reaction involving a strong acid is that the acid does its acid thing, and we say acids are proton donors. Now you'll notice H2O, H2SO4. H2SO4, of course, is the strong acid, and I wrote H3O+. The reason for that, well, several reasons. One reason for that, of course, is that it's easier to write, and we can be a little bit lazy, especially if we don't specifically remember the structure of sulfuric acid. But the other thing that it does is it shows that we remember that when you put water into a strong acid, or vice versa, in fact you should do it the other way, add the strong acid to the water, what happens? It completely dissociates. So into what? H3O+, and the conjugate base of your strong acid. So we're not only being lazy, but we're showing that we're smart. So this strong acid will protonate the alkene. The way that happens, the alkene bond breaks, those electrons grab the hydrogen-oxygen bond breaks, those electrons go back to the oxygen to give us water. That will give us a carbocation. We're breaking the pi bond away from two carbons, and we're going to bond one of those carbons to this hydrogen. And we have a choice. If we put the hydrogen, and let's just draw at least the molecule without the pi bond. So with no pi bonds, we now have two carbons that could be carbocations. And we decide where to put this hydrogen based on the kind of carbocation that we want. We say more highly substituted is more stable for carbocations, radicals, and alkenes. And so we want to put that positive charge where it's going to be most stable. It's most stable where it's most substituted. That would be the secondary carbon. If we put the plus here, it's because we're saying it doesn't get this hydrogen. And so we'll add that hydrogen there. The next step to do is to use our nucleophile. And notice we've also produced water in this step. Although it does, even if we used H2SO4, there's still plenty of water around. We always use an excess in hydration. That will act as our nucleophile and attach to the carbocation. After that happens, we're almost finished. We've added our water, we've added OH. We really only want to add OH, and we've added OH2, which means that we have technically finished with a protonated finished this step at least with a protonated alcohol. And we want simply an alcohol instead. So what do? We need something to act like a base to take off that extra hydrogen. The most readily available good base will be yet another equivalent of water. Although if we used H2SO4 here, created HSO4-, we could use that HSO4- to pick up the hydrogen, become sulfuric acid again, and that would show us that this sulfuric acid is actually a catalyst in the reaction, which is to say that it is participating in the mechanism, but it's not consumed during the mechanism. It's regenerated at the end so that it could be used again. And to pick up that extra hydrogen, all we have to do is use the water's lone pair to make a bond to the extra H, break that HO bond, and dump those electrons back on the oxygen. That will give us our final product. In this case, the major product will be the Markovnikov, the product of Markovnikov addition. In this case, 2-propanol or isopropanol. So we've added OH to the more substituted carbon. We've added hydrogen to the less substituted carbon. We will see some of the other product, but it will be a minor product.